Have you ever stopped to think why water, something so common, boils way up at 100 degrees Celsius? But then methane, which seems kind of similar in size, boils at what, minus 161 degrees? That's a massive, massive difference.
Yeah, it's pretty fascinating, isn't it?
Mm.
And understanding why really gets you into the fundamentals. These basic differences in how molecules, talk to each other, they dictate pretty much everything around us.
Absolutely. Welcome, everyone, to the Deep Dive, your shortcut to being truly well-informed. Today, we're doing a foundational deep dive, really getting into the core of organic chemistry. We're using insights from David Klein's Organic Chemistry, the third edition.
Good stuff in there.
Totally. And our mission today is to unpack the key ideas from Chapter 1, a review of general chemistry, electrons, bonds, and molecular properties. So we'll look at how atoms connect, why molecules have the shapes they do, and importantly, how this basic stuff explains everything from, I don't know, how drugs work, to why geckos can climb walls.
Yeah, it's not just abstract theory. It really is the blueprint for understanding the molecular world.
Okay, so let's maybe kick off with a bit of history. For a long time, people had this idea of vitalism.
Ah, vitalism.
Right.
The idea that organic compounds, stuff from living things, had some kind of special vital force.
Exactly, and that you couldn't make them from, like, inorganic rocks and minerals.
But then Friedrich Schiller came along in 1828, German chemist. And he did something pretty revolutionary. He took ammonium cyanate, definitely an inorganic salt, and he heated it up, and bam, he got urea.
Urea, which is totally organic, found in urine.
Exactly. So making an organic compound from an inorganic one, that was a huge blow to vitalism. It really shifted the definition. Organic compounds became simply those containing carbon atoms. End of story for the vital force, pretty much.
It's funny, though, because even though carbon defines organic chemistry, the real subject seems to be electrons, doesn't it?
Oh, absolutely. At its heart, organic chemistry is the study of electrons. How they move, where they are, where they're likely to go in a reaction. Understanding electron flow is, well, it's everything.
Which leads us nicely into the structural theory of matter.
Right. This is the fundamental idea that what makes a substance what it is isn't just the atoms it has, but the specific way they're connected, the arrangement.
Like dimethyl, ether, and ethanol, you mentioned those.
Perfect example. Both have the same formula, C2H6O, same atom, same count, but connect them differently.
And you get totally different things. One's a gas, one's a liquid at room temperature. Dimethyl ether is the gas, ethanol, the liquid.
Precisely. And these are called constitutional isomers. Same formula, different connectivity. It just hammers home how vital that arrangement is.
So how do we know how things should connect? Are there rules?
There are. And the most basic rule is valency. You have to know how many bonds atoms typically form. Carbon makes 4 bonds tetravalent. Nitrogen makes 3 in trivalent. Oxygen makes 2 divalent. Hydrogen and the halogens, like fluorine or chlorine, just 1 monovalent.
It's kind of like Lego bricks, isn't it? With different numbers of connection points.
That's a great analogy, actually, yeah. Knowing the valency is your first step in building or, drawing a molecule correctly. It's fundamental.
Okay, so atoms connect with a certain number of bonds. What is the bond, though? What holds them together?
Right, so now we're talking about the glue. It's electrons, specifically shared electrons. Gilbert Lewis, back in 1916, he defined the covalent bond as 2 atoms sharing a pair of electrons.
Sharing electrons, how does that hold them together?
Well, think about 2 hydrogen atoms coming together to make H2. Each has 1 proton in the nucleus and 1 electron. As they get closer, the electron of one atom starts getting attracted to the nucleus of the other atom, and vice versa.
Ah.
At the same time, the 2 electrons repel each other, and the 2 nuclei repel each other. Bonding happens when the atoms find that sweet spot, that perfect distance, where the attractions outweigh the repulsions. The system's energy drops.
And that lowest energy point defines the bond length and strength.
Exactly. For H2, it's about 0.74 angstroms long, and it takes about 436 kilojoules per mole to break it. That energy release is what makes the bond stable.
So to visualize all this, we use Lewis structures.
Lewis structures, yes.
Yeah.
They're our way of mapping out the valence electrons, the outermost ones. Those are the electrons involved in bonding. You find the number of valence electrons from the group number in the periodic table.
And there's a key rule for drawing them, especially for elements like carbon, nitrogen, oxygen.
The octet rule.
Yeah.
Super important for those second row elements. They want to achieve 8 valence electrons, like the nearest noble gas, which is a very stable configuration. Hydrogen is happy with 2, like helium.
So if nitrogen has 5 valence electrons but wants 8, it forms 3 bonds.
Right. Sharing 3 electrons from other atoms gives it access to 8 total. And those original 5 valence electrons. 3 are used in bonding, and 2 remain unshared. That's a lone pair.
And those lone pairs matter.
Oh, hugely. They affect the shape of the molecule, its reactivity. Very important. Drawing Lewis structures correctly, making sure everything has the right number of bonds and satisfies the octet rule, that's a foundational skill. Like in Skill Builder 1.3 in the book, remember, you're sharing existing electrons, not inventing new ones.
But what if an atom in a structure doesn't end up with the number of electrons it normally has based on its valence electrons? Like, if it seems to have gained or lost some?
Good question. That's where formal charge comes in. It's a way to keep track of electron ownership, kind of. You compare the valence electrons an atom should have as a neutral atom to the number of electrons it owns in the Lewis structure, meaning all its lone pair electrons plus half of its bonding electrons.
So if nitrogen normally has 5 valence electrons, but in a structure it only effectively owns 4.
Then it has a formal charge of +1. It's lost an electron, essentially. Or if oxygen, which normally has 6, owns 7 in a structure, it has a formal charge of -1. Identifying these charges is crucial because they highlight centers of positive or negative charge, which tells you a lot about potential reactivity. Skill Builder 1.4 covers calculating these.
Okay, so we have atoms sharing electrons in covalent bonds, but is that sharing always equal?
No, definitely not always equal. Some atoms are greedier than others when it comes to electrons.
Greedier.
Well, more formally, we call it electronegativity. It's a measure of an atom's ability to attract the electrons within a bond towards itself. Linus Pauling came up with a scale for this. Fluorine is the king, the most electronegative. Oxygen and nitrogen are high up there too. Carbon and hydrogen are sort of middle of the road.
And this difference in greediness or electronegativity affects the bond.
Absolutely.
Yeah.
It lets us classify bonds. If the electronegativity difference between two bonded atoms is really small, less than about 0.5 on the Pauling scale, like between carbon and carbon or carbon and hydrogen, we call it a covalent bond or sometimes nonpolar covalent, the sharing is pretty equal.
Okay.
If the difference is moderate, say between 0.5 and 1.7, like between carbon and oxygen or carbon and chlorine, the electrons get pulled more towards the more electronegative atom. This creates a polar covalent bond.
Polar, meaning it has poles,
Yeah.
like a positive and negative end.
Exactly. The more electronegative atom gets a slight negative charge, we write it as delta minus a day, and the less electronegative atom gets a slight positive charge, delta plus, plus is plus. This pulling of electrons through the sigma bond is called induction.
And if the difference is really big,
Greater than about 1.7, like between sodium and oxygen, the electron is basically transferred from the less electronegative atom to the more electronegative one. That forms an ionic bond. You have a full positive ion and a full negative ion. But remember, these numbers, 0.5 and 1.7, they're just guidelines. It's really a spectrum from pure covalent to pure ionic.
can you actually visualize these partial charges?
You can. Chemists use electrostatic potential maps. These are computer-generated models that color the surface of a molecule based on charge distribution. Red usually means electron-rich, so partial negative charge, and blue means electron-poor, partial positive charge. They're really useful for seeing where the reactivity might lie.
Okay, so we have bonds within molecules, some polar, some not. But what about interactions between molecules? Why do molecules stick to each other at all? That relates back to boiling points, right?
Exactly right. Those interactions between molecules are called intermolecular forces, or IMFs. They're the forces that hold liquids and solids together. They're weaker than covalent bonds, but crucial for physical properties. And they're all electrostatic in origin attractions between positive and negative charges, whether full or partial.
So what kinds are there?
Well, the first type arises directly from those polar bonds we just talked about. If a molecule has an overall separation of charge, a positive end and a negative end, meaning it has a net dipole moment, then the positive end of one molecule will be attracted to the negative end of another. These are dipole interactions.
Like with acetone.
Acetone is a good example. It has a polar CO bond, leading to a net dipole moment. So acetone molecules stick together relatively well, giving it a boiling point of 56 degrees C. Compare that to isobutylene, similar size but nonpolar, boils way down at -7 degrees C. The dipole forces make a difference.
Okay, what else?
Then there's a special extra strong kind of dipole force called hydrogen bonding. This happens when you have a hydrogen atom bonded to a very electronegative atom, primarily nitrogen, oxygen, or fluorine. That makes the hydrogen very electron poor, very plus atom.
So it's like an exposed proton almost?
Almost, yeah, very partially positive. And this air plus hydrogen is then strongly attracted to a lone pair of electrons on another N, O, or F atom in a nearby molecule. That attraction is the hydrogen bond.
How, like in water, or ethanol versus that dimethyl ether example.
Exactly. Ethanol has an OH bond, so it can hydrogen bond with other ethanol molecules. Dimethyl ether doesn't have an H directly attached to O, so it can't. That's why ethanol boils so much higher, 78 degrees C, than dimethyl ether, negative 24 degrees C, even though they're constitutional isomers with the same atoms.
Wow, so hydrogen bonds are pretty strong then.
Strong for an intermolecular force? Yes. Maybe around 20 kilojoules. Still much weaker than a covalent bond, which might be 400 kilojoule or more. But when you get many hydrogen bonds acting together, like holding the two strands of DNA together, they become incredibly significant. Strong enough to hold the structure, but weak enough to be unzipped when needed. Okay, dipole, hydrogen bonding. Any others? What about totally non-polar molecules? How do they stick together? Good question. Even nonpolar molecules experience attractive forces. These are called London dispersion forces, or sometimes van der Waals forces, though that term can be broader.
London dispersion, how do those work?
Well, electrons are always moving, right? Even in a nonpolar molecule, at any given instant, the electrons might randomly happen to be more on one side of the molecule than the other. This creates a fleeting temporary dipole.
Just for an instant.
Just for an instant. But that temporary dipole can then induce a similar temporary dipole in a neighboring molecule, leading to a brief attraction. These forces are weak individually, but they exist between all molecules, polar or nonpolar.
And they add up.
They add up. And they become more significant for larger molecules because larger molecules have more electrons and larger surface areas. More surface area means more points of contact for these temporary attractions. That's why larger hydrocarbons, like octane, are liquids, while smaller ones, like methane, are gases. More surface area, stronger London forces, higher boiling point.
What about shape? Does branching matter?
It does. If you have two isomers with the same molecular weight, the more branched one will generally have a lower boiling point. Think of spheres versus rods. Rod-like molecules can line up and have lots of surface contact. Sphere-like branched molecules have less surface area available for interaction. So branching decreases London dispersion forces.
This brings us to that gecko example, right? How do they use these forces?
Yeah, the gecko feet. It's a fantastic example of London dispersion forces in action. Geckos don't use glue or suction cups. Their feet are covered in billions of incredibly tiny hairs called setae, which branch further into even tinier spatulae. Billions. This creates an absolutely enormous surface area that makes intimate contact with the wall or ceiling. Even though London forces are weak individually, the sheer number of contact points generates enough collective force to hold the gecko up. It's all about maximizing surface area for those weak universal attractions.
That's incredible. Biomimicry right there.
Totally. People are trying to create materials that mimic this, maybe gloves that let you climb walls. It all comes back to understanding these fundamental forces. So when you predict physical properties, like in Skill Builder 1.10, you have to weigh all these factors: dipole, hydrogen bonding, molecular weight for London forces, and branching.
Okay, this is great for understanding interactions, but to really grasp bonding and shape, we need to go deeper into orbitals, quantum mechanics.
To really understand why bonds form and why molecules have specific 3D shapes, we need to think about electrons as waves, described by quantum mechanics. The solutions to the Schrödinger wave equation give us wave functions, usually represented by the Greek letter Ci.
And the wave function tells us?
Well, the wave function itself isn't directly physical, but its square gives us the probability of finding an electron in a particular region of space. These regions of high probability are what we call atomic orbitals, AOs, like the SPDF orbitals you learned about in general chemistry.
Right, S orbitals are spherical, P orbitals are dumbbell-shaped.
Exactly, and they have phases, often shown as shaded or unshaded regions, or plus and minus signs. This phase is important for how orbitals interact when bonds form. We fill these orbitals with electrons following specific rules.
Like the Aufbau principle.
Right, Aufbau principle. Fill lowest energy orbitals first. Pauli exclusion principle. Maximum 2 electrons per orbital, and they must have opposite spins. And Hund's rule, put 1 electron in each orbital of the same energy, degenerate orbitals, before pairing them up. Skill Builder 1.6 is about using these defined electron configurations.
So how do these orbitals explain bonding?
Well, one model is valence bond theory. It views a covalent bond as forming when atomic orbitals on adjacent atoms overlap constructively, meaning regions with the same phase overlap. This overlap, typically end-on-end along the axis connecting the two nuclei, forms a sigma. forms a sigma bond.
Just overlap of atomic orbitals. Seems simple enough.
It's a useful model, but a more sophisticated and often more accurate picture comes from molecular orbital, MO theory. In MO theory, when atomic orbitals overlap, they actually cease to exist and combine to form entirely new molecular orbitals that belong to the entire molecule.
So orbitals aren't localized between just two atoms anymore.
Not in the pure picture, no. Combining atomic orbitals creates both lower energy bonding MOs, where electrons stabilize the molecule, and higher energy antibonding MOs, often marked with an asterisk, which destabilize it. Antibonding MOs have a node, a region of zero electron density between the nuclei.
And knowing these MOs helps understand reactions.
Immensely. Two key MOs are the HOMO, the highest occupied molecular orbital, and the LUNOMO, the lowest unoccupied molecular orbital. Chemical reactions often involve electrons flowing from the HOMO of one molecule, where the least tightly held electrons are, to the LUMO of another molecule, the lowest energy empty spot for electrons to go. Understanding HOMO-LUMO interactions is key to predicting reactivity.
Okay, that's the electronic structure. But how does this explain the 3D shapes we see, like methane being tetrahedral? Carbon's ground state electron configuration doesn't seem to suggest 4 equal bonds.
You're absolutely right, it doesn't directly. To explain the observed geometries, we use the concept of hybridized atomic orbitals. This is basically a mathematical mixing or averaging of the atom's valence atomic orbitals to create new hybrid orbitals that have the correct shapes and orientations for bonding.
So for methane, CH4, carbon needs to form 4 identical single bonds.
Right, so we imagine mixing carbon's 1,2's orbital and its 3 2p orbitals. This mathematical process gives us 4 equivalent C3 hybrid orbitals. These force p3 orbitals naturally point towards the corners of a tetrahedron, which gives the 109.5-degree bond angles we observe in methane. Perfect match.
Okay, what about double bonds, like in ethylene C2H4?
In ethylene, each carbon is bonded to 3 other atoms, 2 H's and the other C. So it needs 3 equivalent orbitals. We mix the 2's and 2 of the 2p orbitals to create 3 sp2 hybrid orbitals. These sp2 orbitals lie in a plane and point towards the corners of an equilateral triangle that's trigonal planar geometry with 120-degree angles.
Well, what about the peak orbital that wasn't used?
That unhybridized orbital is still there, sticking straight up and down perpendicular to the plane of the sp2 orbitals. When 2 cp2 hybridized carbons form a double bond, one bond is a sigma bond formed by the overlap of sp2 orbitals head-on. The other bond is a pi, formed by the sideways overlap of those leftover parallel p orbitals above and below the sigma bond axis. So double bond is 1 sigma and 1 pi bond. Correct. And for a triple bond, like in acetylene, C2H2, each carbon is bonded to only 2 other atoms, 1H, 1C. So it needs 2 hybrid orbitals. We mix the 2's and just 1 2p orbital to get 2 sp hybrid orbitals. These point in opposite directions, giving a linear geometry with 180-degree angles.
And the leftover p orbitals. There are 2 this time.
Exactly. 2 unused p orbitals remain on each sp hybridized carbon, perpendicular to each other and to the bond axis. These overlap sideways to form 2 pi bonds. So a triple bond consists of 1 sigma bond and 2 pi bonds.
That makes sense why triple bonds are stronger and shorter than double, and double are stronger and shorter than single. You have more overlapping orbitals holding the atoms together. Skill Builder 1.7 helps identify these hybridization states quickly.
Precisely. It's a very powerful model for connecting bonding to geometry.
Is there a quicker way to predict the shape without thinking through hybridization every time?
Yes, there is. VSEPR Theory, valence shell electron pair repulsion theory. It's simpler and often works very well. The core idea is that electron pairs, whether they're in bonds, bonding pairs, or lone pairs, repel each other electrostatically. So they arrange themselves around a central atom to be as far apart as possible to minimize that repulsion.
So you just count the electron groups?
Pretty much. You count the number of sigma bonds plus the number of lone pairs around the central atom. That sum is called the steric number. The steric number tells you the arrangement of the electron pairs. Steric number 4 means the electron pairs adopt a tetrahedral arrangement like methane, ammonia, water. Steric number 3 means trigonal planar, like BF3 or ethylene's carbons. Steric number 2 means linear, like BH2 or acetylene's carbons.
But the molecular geometry of the shape based on the atoms might be different if there are lone pairs, right?
Exactly. Methane, CH4, steric number 4, no lone pairs, has tetrahedral electron geometry and tetrahedral molecular geometry. Ammonia, NH3, steric number 4, 1 lone pair, has tetrahedral electron geometry, but the atoms form a trigonal pyramidal shape. Water, H2O, steric number 4, 2 lone pairs, has tetrahedral electron geometry, but the atoms make a bent shape. The lone pairs influence this shape and often compress the bond angles slightly.
So VSEPR is a really useful predictive shortcut. Skill Builder 1.8 focuses on this.
It is. It's a model, so it has limitations. For example, it treats lone pairs in water as equivalent, which more advanced calculations show isn't quite true, but it's remarkably effective for predicting basic shapes.
And knowing the 3D shape is crucial for understanding if the whole molecule is polar, right? Not just individual bonds.
Absolutely. A molecule has an overall molecular dipole moment if the individual bond dipoles don't cancel each other out due to symmetry. It's a vector sum.
Like carbon tetrachloride, CCO4. It has 4 polar CCl bonds.
But it's perfectly tetrahedral. The 4 bond dipoles point to the corners of the tetrahedron and they perfectly cancel each other out. So CCl4 is a nonpolar molecule overall. Chloromethane, CHUCl, however, also tetrahedral, is polar because the CCl dipole isn't canceled by the CH dipoles.
And lone pairs contribute too.
Significantly. The lone pair on nitrogen in ammonia contributes to its overall dipole moment. So geometry is key. You need to know the bond polarities and the 3D shape to determine if a molecule will have a net dipole moment, which Skill Builder 1.9 helps with. Understanding this is vital, especially for things like the CO double bond, which is very polar and reactive.
Okay, so all these ideas, polarity, IMFs, shape, they all come together in practical ways, right? Like solubility.
Yes, the classic rule, like dissolves like.
Yeah.
Polar molecules tend to dissolve well in polar solvents, like
Right.
water or ethanol, and nonpolar molecules dissolve well in nonpolar solvents, like hexane or carbon tetrachloride.
Why is that?
It's all about maximizing those favorable intermolecular interactions. Polar solvent molecules have strong dipole or hydrogen bonding interactions with each other. For a polar solute to dissolve, it needs to be able to form similarly strong interactions with the solvent molecules to overcome the solvent attractions. Nonpolar solutes can't do that, so they get excluded. Similarly, nonpolar molecules interact via London forces, and they mix well with other nonpolar things where they can maintain those interactions.
Like dissolves like.
Yeah.
Makes sense. Can you give some examples?
Sure. Think about soap. Soap molecules are amazing. They have a long, nonpolar hydrocarbon tail, hydrophobic water-fearing, and a polar or ionic head group, hydrophilic water-loving.
So one end likes oil, the other likes water.
Exactly. When you wash greasy hands, the nonpolar tails of the soap molecules surround the nonpolar grease particles, burying themselves inside, while the polar heads stick out facing the water. This forms a structure called a micelle.
Ah, like a little ball of soap with grease trapped inside.
Precisely. And because the outside of the micelle is covered in polar heads, the whole thing becomes soluble in water and gets washed away. Genius chemistry.
What about dry cleaning?
Dry cleaning is another perfect example. It uses nonpolar solvents, like tetrachloroethylene, specifically because they can dissolve nonpolar stains like grease or oil, that water, being polar, can't remove effectively, like devolves like.
And you mentioned a medical example, propofol.
Yeah, propofol is a widely used anesthetic. It's the drug notoriously linked to Michael Jackson's death. Propofol itself is largely hydrophobic, nonpolar. It doesn't dissolve well in water or blood plasma.
So how do they inject it intravenously?
They formulate it. They mix the propofol with soybean oil, also nonpolar, and then add lecithins. Lecithins are emulsifying agents, similar to soap, in that they have both hydrophobic and hydrophilic parts. They form micelles that encapsulate the oily propofol mixture.
So they make tiny packages of propofol that can mix with blood.
Exactly. The result is a milky white emulsion that can be safely injected. Once in the bloodstream, the propofol can easily leave the micelles and, being hydrophobic, readily cross the fatty membranes of brain cells to exert its anesthetic effect. It's a brilliant application of controlling solubility for drug delivery.
Wow. So these fundamentals, electrons, bonds, polarity, shape, IMFs, like they really are everywhere.
They really are. They explain how drugs fit into receptors in our bodies, often involving lots of weaker interactions like hydrogen bonds and London forces, kind of like a flexible lock and key. They explain the properties of materials, why things dissolve or don't dissolve. It all comes back to these core principles from Chapter 1.
And that wraps up our deep dive into these foundational principles of organic chemistry from Klein's first chapter. We've journeyed from the idea of vitalism all the way to the quantum world of orbitals and seen how the invisible dance of electrons dictates, well, pretty much everything tangible.
Absolutely. Understanding valency, Lewis structures, formal charge, electronegativity, intermolecular forces, hybridization, VSEPR, these aren't just isolated concepts. They're the interconnected tools you need to understand the structure, properties, and reactivity of molecules. It's the essential toolkit for navigating organic chemistry.
It really shows how this knowledge isn't just theoretical, it's fundamental to understanding the chemistry that literally makes up our world and our bodies.
Couldn't fit it better myself.
So, a final thought for you to ponder as you go about your day. What other everyday things that you maybe take for granted, the stickiness of tape, the smell of rain, the way sugar dissolves in coffee, can ultimately be traced back to these precise rules governing electrons, bonds, and molecular shapes? The chemical explanations are out there.
Thank you for joining us on this deep dive. It's been great exploring these ideas.
It has indeed. Until next time, keep exploring and stay curious.